So we already studied the concept of function of a random variable, and this sum of two random variables is somewhat similar to that of that constant. But here we have a random variable z, which is obtained by summing up the two random variables x and y. So here the assumption is x and y are statistically independent random variables. These two are independent. So here we can say that sum of two independent random variables. Here x is the random variable with density function fx of x, and y is another random variable density function fy of y. So here our aim is to find the density function of the random variable z in terms of the density function of x and density function of y. That is, we have to find the fz of z. So what is this? What is the relationship between the density function of the random variable z, density function of the random variable x, and the density function of the random variable y, given z is the sum of two random variables x and y. So we try to derive an expression for fz of z in terms of fx of x and fy of x. So for that purpose, we take the xy plane. So which is the joint sample space of the two random variables. So here if z is equivalent to x plus y, you can write small z is equivalent to small x plus small y, where small z is the value that taken by the random variable z, and similarly x and y. So here when x is equivalent to 0, y is equivalent to z. That is, this point is z. Similarly, when y equivalent to 0, x is also z. So here if you consider an equation that is y is equivalent to z minus x. So if you take this expression in the form of y equivalent to some yx plus c. It's an equation of straight line. It passes through these two points. Is it? Therefore, so here I can say that this straight line can be represented as y is equivalent to z minus x. Understood? In the form of y equivalent to some mx plus c form. Understood this? So here, to find the fz of z, that is the density function of the z, first of all we have to find fz of z. That indicates we have to define the event z less than or equivalent to z. So if you know, or if you define this event on this space, and if you evaluate the density function, that is the probability of this event, then we can get the CDF. If you know the CDF, by differentiating CDF, we can evaluate the probability density function of the random variable z, which is equivalent to x plus y. So here, this line, this straight line is equivalent to z. Is it? See, everywhere the point on this line is equivalent to z. Is it right? Z is equivalent to x plus y. So therefore, if you take this event mod z less than or equivalent to z, that is this entire region, that is the region below this straight line, corresponds to the event z less than or equivalent to z. So here I can write this region indicates the event z less than or equivalent to z. Now we have to find the probability of this particular event. Then we can find fz of z. So here, can I write the CDF of the z as fz of z is equivalent to integral minus infinity to plus infinity integral minus infinity to x, which is equivalent to, what is x in this case? Z minus 1. And this is fxy of x comma y dx dy. Is it right? With the assumption that this fxy of x comma y is the joint density function of the two random variables x and y. If you know the joint density function of the two random variables, then we can find this fz of z. Why? Because fz of z, that is z, x and y are related by this equation. Therefore, fz of z can be written as minus infinity to plus infinity. That is, here y is equivalent to minus infinity to plus infinity, and I am taking x. X is from minus infinity to z minus 1. That is this line. Understood? Otherwise, you can take x equivalent to minus infinity to plus infinity, y is equivalent to minus infinity to z minus x. Either way you can take. Understood? That is, we are keeping the y, we are assuming y is taking minus infinity to plus infinity, and x, that is this range, which is taking the values from minus infinity, that is left side, to this point. What this point indicates, that is this line. I assume y is taking values from minus infinity to plus infinity, x is from minus infinity to x. In this case, x is z minus y. So that's what I written it as minus infinity to x, which is equivalent to z minus y of xy dx. That is, if you integrate the density function twice, you will get fz of z. Actually, what you will get fxy of x comma y. Okay, but here z is related to x and y, so that's why we are writing this as fz of z, with the assumption that we consider this region, the region in which z is less than or equal to z. So that event corresponds to fz of z. Are you following why I have written the left hand side as fz of z? Actually, the left hand side should be fxy of x comma y, capital fxy of x comma y, joint CDF. But here the region of our interest is mod z less than or equal to z. So that's why I have written it as fz of z, and which is equal to this. So this step is very, very important. We consider the region below this, that is y equivalent to z minus x, or x equivalent to z minus y. Either way you can take. Because we have taken the xy plane, x and y are two random variables. We know the values that are taken by the x and the values that are taken by the y. And we are trying to find the density function or the distribution of the random variables z, which is equivalent to x plus y. For that purpose, we use this relation, z is equivalent to x plus y, or y equivalent to z minus x, or x equivalent to z minus y. Either way you can. And this integral can also be written as y equivalent to minus infinity to z minus x, minus infinity to plus infinity, like that also you can write. Now take the same equation, so fz of z, which is equivalent to minus infinity to plus infinity, and here I separate this inner integral, minus infinity to x, z minus y. Here I write this inside fxy x comma y dx, because this integral is minus infinity to x, that is, this integral is with respect to ls. So here I am writing this, I am separating the two integrals. Then the inner integral, you see the inner integral, we are integrating with respect to x only. The integrand is joint density function. If you integrate the joint density function with respect to a one variable, either x or y, what you will get? We will get the marginal density. Otherwise, can I write this as fxy? Here y is same, y is not varying, but x is changing. What is the upper limit here? Upper limit is z minus y, comma y minus fxy. The lower limit of x is minus infinity. The upper limit of y is y. In this inner integral, okay, if you see the inner integral, y is constant. That is, we are not changing the y value. So that's we are keeping y as it is. But x is taking two limits, the upper limit and the lower limit. So integral minus infinity to x fxy of x comma y dx. Okay, that can be written as fxy of upper limit comma y and fxy of minus infinity comma y. Obviously, the second term is equivalent to 0 because it is the joint probability. The probability of x less than or equivalent to minus infinity and y less than or equivalent to 1. So it is uncertain event. So it is 0. Therefore, this can be written as minus infinity to plus infinity. And we have fxy z minus y of y dy. If you observe this integrand is a function of x and z, sorry, y and z. Is it z minus y and y? It is function of z and y. We are integrating with respect to y. So after integration, it will become function of z. So left hand side is a function of z, right hand side is also function of z. So this is the density function, sorry, distribution of the random variable z. So if you know this, can we find the density? To simply differentiate. What is fz of z? Fz of z is equivalent to d by dz. Because this function, both the left hand side and the right hand side functions of z. So that's why we are differentiating with respect to z on both sides. Then you substitute this integral here, change the order of integration and differentiation, bring the differentiation inside the integral. Then you can write it as minus infinity to plus infinity. So derivative of this, the derivative of inner one is z minus y comma 1. And if you take the inner one, you will get 1. So it is again see the integrand is function of z and y. We are integrating with respect to y. So after integration, the right hand side is a function of z, which is equivalent to function of z in the left side. But we are assumed that this fxy of z minus y comma y is equivalent to, see what is z minus y actually? Z minus 1 is equivalent to x, that is fxy of x comma y. This can be written as fx of x into fy of y. Why? Because the assumption is the two random variables are statistically independent. X and y are statistically independent. Z is sum of two statistically independent random variables. So if the two random variables are independent, then fxy of x comma y is equivalent to fx of x into fy of y. Therefore, this can be written as minus infinity to plus infinity fx of z minus y fy of y g. Now, if you observe this integral is in the form of integral minus infinity to plus infinity f of tau some g of t minus tau d tau. This is the convolution between the two fx of x and fy of x. Understood? Why I am writing it as fx of x? Because this z minus y is equivalent to x. Therefore, I can write it as fx of x convolution with fy of. What this indicates? If you know the sum of two random variables, two independent random variables, and their densities, that is the density of x and y, we can find the density of z by simply convolving the density functions of the two random variables x and y. The probability density function of the random variable z is equivalent to the convolution between the density function of x and density function of y. Can I write this integral as integral minus infinity to plus infinity fx of x fy of z minus x dx. Is it right? That is, here I have written minus infinity to z minus y. For example, if you take it as plus infinity minus infinity to z minus x, then you will get this expression. Right? What is this? This is fy of y convolution with fx of. We already know that convolution is commutative. So fx of x convolution with fy of y is equivalent to fy of y convolution with fx of. Therefore, this can also be written in this way: fy of y convolution with fx of x. I think you already studied about the properties of the convolution. Convolution is commutative, convolution is associative, and distributive. So here we can use either of the two expressions. Fx of x convolution with fy of y is equivalent to fy of y convolution with fx. So this concept is important, and based on this we study the central limit theorem. In the next class we consider the central limit theorem, which is based upon this relation. Here we consider the sum of two random variables. Can we extend to n random variables? For example, we have sum of n statistically independent random variables. Then we can find the density function of the z. So here z can be considered as x1 plus x2 plus 1 xn, n number of random variables. Then we can find the density function of the z. We see how can we do it. We extend this concept to n random variables. Sum of n random variables. So let us take this z is equivalent to x1 plus x2 plus x3. I am considering three random variables in this case for example. Now can I write it as x plus y, that is x1 plus x2 is x and x3 is y. Therefore, what is fz of z? Fz of z is equivalent to fx of x convolution with fy of y. But we already assumed that this x equivalent to x1 plus x2. See, x1 and x2 are statistically independent. that x plus y is all x plus y plus x3 is also statistically independent. Understood? X plus x1 plus x2 plus x3. These three are independent random variables. Now we are taking x1 plus x2 as x. Then x and x3 also statistically independent because x is equal to x1 plus x2. Therefore, both x and x3 are statistically independent. Or x and y are also statistically independent. Therefore, fz of z can be written as fx of x convolution with fy of x. But what is fx of x? This can be written as fx1 convolution with fx2 and fy of y equivalent to fx2. So therefore, here can I replace this fx of x by fx1 convolution with fx2 convolution with this is fy of y. What is fy of y? Fy of y is equivalent to fx of y. Here for simplicity I written this as, that is fx1 of x1 is written as simply fx1. Similarly fx2 of x2 as fx2. I removed that brackets. So many brackets are there. So now can I change this to fx1 convolution with fx2. Convolution is associated. This is for three random variables. Now let this z is equivalent to x1 plus x2 and so on x n. That is, we have n statistically independent random variables, where z is the sum of these statistically independent random variables. Then fz of z is equivalent to convolution of the density functions of x1, x2, so on x. Therefore, this can be written as fx1, fx2, convolution with the last term is fxn. So that is, fx1 is the density function of the random variable x1, fx2 is the density function of the random variable x2, fxn is the density function of the random variable xn, and density function of the random variable z, which is equivalent to x1 plus x2 plus 1 xn, is given by convolution of the density function of these random variables x1, x2, so on. So this is the density function of sum of n statistically independent random variables. The density functions of two random variables x and y are shown. So this is the density function of the random variable x, 0, 1, this is also 1. Is it right? What is the area? 1. In both cases it is 1. Both are valid density functions. Shown below. Find the density function of a new random variable z is equivalent to x plus 1. Z is equivalent to x plus 1. That is, x and y are two independent random variables. Z is the sum of two independent random variables. The density functions of x and y is given. You have to find the density function of z. So how you do it? We already know that this fz of z is equivalent to fx of x convolution with fy of y. That is, you have to convolve these two. we know how to do the convolution between the two functions to find the convolution. Can you do it? Two functions are given. Find the convolution between those two, which will be the density function of the random variable z.